Knowing how much you all love trigonometry and love solving trigonometric equations, I thought it might be a great time for us to look at solving this beautiful trigonometric equation. So a lot of terms, a lot of stuff to keep track of. Let's get right into it. So first thing that we might notice or remember when we're solving an equation like this is that we're looking for opportunities to use identities, because identities really allow us to simplify expressions using relationships that are either from the unit circle or identities from the formula sheet that you're required to know. So the first one that you might think about is cosine of 2x. Now, one really useful identity for cosine is that when we have cosine of 2x, cosine of 2x is equivalent to 2 cosine squared of x minus 1. Now, why would I choose to use that one? Well, looking at what we have here, we have a sine squared x, we have a cosine squared of x, we have another cosine. It might be wise to try to look for ways to get everything in terms of just cosine, if possible. So it's not totally clear that this identity is going to work for us, but let's hold this in our back pocket just until we're sort of sure that this might be useful for us. The other one, just sort of noticing that we have a sine squared x here and a negative cosine squared of x there. If I move this to the other side, it's kind of tempting to potentially use sine squared x plus cosine squared of x being equal to 1. Because again, that's two terms. It can be reduced down to a single term. So rewriting this equation, cosine of 2x minus 3 cosine of x minus 3. And if I set that equal to sine squared of x plus cosine squared of x, I can use the first identity, this one right here, to simplify this expression. Okay, so that'll make things better. And I also can use the fact that cosine of 2x is equal to 2 cosine squared x minus 1 to rewrite this term. So if I do that, I get 2 cosine squared of x minus 1 minus 3 cosine of x minus 3 is equal to 1. All right, so this is looking really nice. So now that we have that, let's simplify things up a bit. So 2 cosine squared of x, I have minus 3 cosine of x, and then noticing that I have a couple constant terms, this becomes minus 5 is equal to 0. Now there are two things that you could do at this stage. You might notice that this is a quadratic in cosine of x. So one thing, the reason that might be important to you is that one thing you could do is realize that this expression we might be able to write as a pair of binomials. Specifically, this could be 2 cosine of x minus 5 times the quantity cosine of x plus 1 is equal to 0. How do we know we can do that? Let's say that didn't jump out at you as a possibility, so it wasn't totally clear that that would be a useful step. What you could instead do, let's just do this kind of on the side here, is try making a substitution. Let's say that we decide to say u is equal to cosine of x. This is not a calculus u substitution. I'm just using u because it's a variable, it's convenient, no big deal. So that turns this equation then into 2u squared minus 3u minus 5 is equal to 0. And this is just a friendly neighborhood quadratic. How do you know if you could factor this? Well, this is where the discriminant comes in. The discriminant we get, we know, is b squared minus 4ac. And we can calculate this out. B for this quadratic is negative 3, so we're going to square that, minus 4 times a, which is 2, times c, which is negative 5. So this becomes 9 minus 4 times 2 times negative 5, which becomes plus 40, or just 49. And when the discriminant is a perfect square, we should get excited because perfect square means that we can factor this. Okay, factoring a quadratic is always preferable to using the quadratic formula if we can. So now that we have that, we could use quadratic formula. We could try factoring it into 2u minus 5 times u plus 1. Okay, so that's equal to 0. From that, we get that u is equal to 5 halves, and also that u is equal to negative 1. Now, let's spin around back to what would have happened if we were doing this just with the quadratics. The same sort of thing would happen. We're setting each factor equal to 0, and so we would still get that cosine of x is equal to 5 over 2, or that cosine of x is equal to negative 1. In either case, what we would do is we would be setting cosine of x to be equal to 5 over 2 or negative 1, because if we were doing this in our u method right here, because u is just cosine of x, we would just be substituting cosine of x in for u. So we would end up with the same result. So now we need to figure out what are the solutions. When, over the interval that we are asked to solve this, that is 0 to 2 pi, when are these two possible things true? Okay, so cosine of x equals 5 over 2. One thing that we need to recognize about cosine of x is that cosine of x is always between negative 1 and 1. Because of that, this equation doesn't actually yield any solutions to our original equation. So let's look at this one. When from 0 to 2 pi is this true? There's actually only one value where this is true, knowing our unit circle, and that is when x is equal to pi. Okay? Now, since there's nothing coming from this leftmost solution, since there's nothing over there, and we only have one solution from this factor of cosine x equal to negative 1, the final solution is that x is going to be equal to pi. And that is our complete solution to this problem.